In this section of the chapter, we're still going to be examining hydrocarbons, but now we are going to look at unsaturated hydrocarbons. Unsaturated hydrocarbons contain one or more carbon-carbon double bonds, triple bonds, or benzene-like rings. So alkenes specifically contain one or more carbon-carbon double bonds. An alkyne contains one or more carbon-carbon triple bonds. A carbon-carbon double bond is depicted as two lines between the two carbons. A carbon-carbon triple bond would look like three lines between the two carbons. These compounds are considered unsaturated hydrocarbons because they do not contain the maximum number of hydrogen atoms. Alkenes and alkynes will react with hydrogen gas to increase the number of hydrogen atoms and become alkanes. So we can take an unsaturated hydrocarbon and make a saturated hydrocarbon. As I said in the previous slide, alkenes contain one or more carbon-carbon double bond. A double bond is depicted as two lines between the carbons. In ethene, two carbon atoms are connected by a double bond. Each carbon atom in the double bond is attached to two hydrogens. There is a trigonal planar arrangement of atoms, and the bond angle is 120 degrees. Compounds containing carbon-carbon double bonds are especially widespread in nature. Ethene, more commonly called ethylene, has enormous commercial importance in our modern industrialized society. The organic chemical industry worldwide produces more pounds of ethylene than any other organic chemical. Annual production in the United States alone exceeds 55 billion pounds. What is unusual about ethylene is that it occurs only in trace amounts in nature. The enormous amounts of it required to meet the needs of the chemical industry are derived the world over by thermal cracking of hydrocarbons. In the United States and other areas of the world with vast reserves of natural gas, the major process for the production of ethylene is thermal cracking of small quantities of ethane extracted from natural gas. From the perspective of the chemical industry, the single most important reaction of ethylene and other low molecular weight alkenes is polymerization. The crucial point is to recognize that ethylene and all of the commercial and industrial products synthesized from it are derived from either natural gas or petroleum, both non-renewable resources. I mentioned the low abundance of ethene or ethylene found in nature. Its role in nature is as an important plant hormone involved in promoting the ripening of fruits such as bananas. It accelerates the breakdown of cellulose in plants, which causes flowers to wilt and leaves to fall from trees. Now, if you know anything about hormones, hormones are present in very trace amounts because just a small bit of hormone has a very large effect. Alkynes contain one or more carbon-carbon triple bonds, and that you can see depicted here. And you can see the difference how a triple bond looks compared to a double bond. In ethine, two carbon atoms are connected by a triple bond. Each carbon atom is also bonded to one hydrogen atom, and that's the case for ethine. Each carbon atom in the triple bond has a linear arrangement with bond angles of 180 degrees. So let's do a learning check. We need to identify the following compounds as an alkene or an alkyne. You can see here we have a carbon-carbon double bond. This would be an alkene. And here we have a carbon-carbon triple bond, and this would be an alkyne. So as we learned how to name alkanes, we are going to learn how to name alkenes and alkynes. The IUPAC names for alkenes and alkynes are similar to those of alkanes. What you are going to do is you are going to identify the parent chain. So the parent chain is the longest continuous chain of carbons. We are going to use the same names. So for example, if we see that we have a double bond, we are going to count the number of carbons. 1, 2, 3, 4, 5, 6. So the parent name will be a hexane. We are going to then change that A-N-E to ene, so that we will have hexene. The next thing we need to do is we need to designate the position of that double bond. So if we count carbons, we want to give the double bond, the first carbon of the double bond, the lowest possible number. So here, this would be 3 hexene. IUPAC convention has changed so that we can also name this compound as hex-3-ene, where we are designating 3 for the carbon-carbon double bond. When naming an alkyne, we'll do the same thing where you find the longest continuous parent chain, and then you change the ending of ANE to YNE, and you designate the position of the triple bond. If the triple bond or double bond are at carbon 1, you do not have to designate the position. So here, if we look at propane and then propene, it would be 1, 2, 3, and propyne, it would be 1, 2, 3. Let's do the following learning check together. Write IUPAC names for each of the following. So let's find the longest continuous chain. 1, 2, 3, 4, 5. I could also label this carbon down here 5, but it would lead to the same result. Now, there is both a double bond and a methyl substituent. In the alkane video, I alluded to a concept known as priority in nomenclature. So, from a priority perspective, a double bond takes precedence over an alkyl substituent. What this means is that it is higher priority. So the longest chain needs to include the highest priority substituent. And as you can see, it does. This is my longest continuous chain, and it contains the double bond. And we are also going to assign the lowest number to the highest priority substituent. So that when we name this, the double bond starts at carbon 2, and we have a methyl substituent at carbon 4. So the name here, the parent will be a pentane. We will change the ANE to ene. So this compound will be 4-methyl 2-pentene, or 4-methyl pent-2-ene. Either name is acceptable. Here we have an alkyne. Let's label the longest continuous chain. 1, 2, 3, 4, 5, 6. Okay, we don't have any other substituents. We want to assign the lowest number to the triple bond. So the parent will be a hexane. We will change the ANE to YNE, or ine. This compound is either considered 2-hex-ine or hex-2-ine. Either is acceptable. The best way to get good at nomenclature problems is to practice them. So here, this is just laying out what I did for you in table format. You need to name the longest carbon chain that contains the double or triple bond. So we have a pentane, which we make a pentene. We have a hexane, and we make it hexine. You designate the position of the unsaturation, either the double bond or the triple bond. And then we need to designate the substituent. So here, it will be 4-methyl 2-pentene, and then 2-hexine. Again, if you want, you can put the number of the double bond in front of the ending, or the number of the triple bond in front of the ending. Both are acceptable ways to name these compounds. 3. Just as we had cycloalkanes, we can have cycloalkenes. Cycloalkenes have a double bond within a ring structure and are named similarly by assigning the double bond to be between carbon 1 and carbon 2 when a substituent is on the ring. You're trying to give the lowest number possible to the unsaturation. In our name, we do not need to include the number of the double bond if it starts at carbon 1. So this ring here has 5 carbons in its longest continuous chain, which is the ring. 1, 2, 3, 4, 5. We have a methyl substituent on carbon 3, so this will be 3-methylcyclopentene. Let's name the following alkenes. So they're both alkenes because they have double bonds. Let's count. 1, 2, 3, 4, 5, 6. So this will be cyclohexene because the double bonds at position 1, we do not need to designate its number. Let's count here. 1, 2, 3, 4, 5. This will be a cyclopentene. I need to number the ring clockwise, so that gives these dimethyl groups the lowest possible number. If we were to number counterclockwise, and I'll show you what I mean by this. So here's our double bond. If we were to call this carbon 1, 2, 3, 4, 5, then those methyl groups would be 5,5 dimethyl. And we can get lower numbers by numbering the way I did on top. So this compound is going to be designated 3,3-dimethyl cyclopentene. Again, we do not need to give a number to the double bond because it is at carbon 1. I would practice the nomenclature problems in the textbook. You will not have anything overly complicated on your exam. The homework might be a little bit more challenging because you have more time to complete it. Now we are going to explore a concept known as geometric isomerism or cis-trans isomerism. We already looked at constitutional isomers or structural isomers. This is where you have the same molecular formula but a different connectivity or structure. When we look at cis-trans isomerism, you're going to have the same molecular formula because that designates an isomer, but you're going to have a different geometric arrangement. In an alkene, the double bond is rigid and does not rotate. Remember, the carbons of the double bond are trigonoplanar, and the bond angle is 120 degrees. This holds the attached groups in fixed positions. It makes cis-trans or geometric isomerism possible when two different groups are attached to the carbon atoms on each side of the double bond. So let's look at the compound 1,2-dichloroethane. If the chlorine atoms are on the same side of the double bond, they are cis to each other. If they are on opposite sides of the double bond, the compound is slightly different. They are trans to each other. Now, you do not need to have the same groups attached to the carbons of the double bond. This is just an example where they happen to be the same. If you have two different groups attached to the carbons of the double bond, you can still have cis-trans isomerism. Cis-trans isomers have different physical and chemical properties. You can make a double bond with your fingers with both thumbs on the same side or opposite each other. Let's look at the cis and trans isomers of butene. In cis-2-butene, the methyl groups are on the same side of the double bond. The melting point for this compound equals negative 129 degrees Celsius, and the boiling point is 4 degrees Celsius. If we look at trans-butene, the melting point is negative 106 degrees Celsius, and the boiling point is 1 degree Celsius. So you can see if the methyl groups are on the same side of the double bond, you have different physical properties than if the methyl groups are on opposite sides of the double bond. Although humans communicate largely by sight and sound, the vast majority of other species in the animal world communicate by chemical signals. Often communication within a species is specific for one or two or more stereoisomers, or geometric isomers. For example, a member of a given species might respond to the cis isomer of a chemical, but not to the trans. Alternatively, it might respond to the precise ratio of cis and trans isomers, but not to other ratios of these same geometric isomers. Pheromones are examples of these chemical signals. Some pheromones may warn an insect of danger, they may mark a trail, or sometimes they can attract the opposite sex. As I stated previously, the effectiveness of many of these pheromones depends upon the ratio of cis or trans molecules to each other. One pheromone, bombacol, is emitted by female silkworm moths, which contains one cis double bond and one trans double bond. So you can see here you have a cis double bond, and here you have a trans double bond. And the ratios or amounts of these hormones in relation to each other will determine how effective the pheromones are. In nomenclature, the prefix of cis or trans is placed in front of the alkene name when the compound has a cis or trans isomer. On the left, we have cis 1,2-dibromoethene. The bromines are on the same side of the double bond. And here on the right, we have 1,2-trans dibromoethene because the bromines are on opposite sides of the double bond. Let's name each using cis or trans prefixes when needed. So the longest continuous chain is 1, 2, 3, 4. The double bond will be at carbon 2. We have a 2,3 dichloro compound. So it would be cis 2,3 dichloro 2-butene. Next, we have bromine substituents. Again, it's 1, 2, 3, 4. This will be trans 2,3 dibromo 2-butene. And then we have 1, 2, 3, 4. Here the methyl groups are trans to each other, so this will be trans 2-butene. I just want to emphasize that the substituents do not always have to be the same. We are going to conclude by looking at addition reactions to alkenes and alkynes. What we are going to do is we are going to learn to add certain molecules across a double bond. Alkenes and alkynes are very reactive. We can add hydrogen gas and water to the carbons in the double or triple bond. Double bonds and triple bonds are easily broken, providing electrons to form new bonds. We haven't had much of a discussion, but the reactions that we've looked at are all about the electrons. We discussed oxidation-reduction reactions, and we looked at a transfer of electrons. And so what we are going to see here is that it's all about the electrons. If we add hydrogen, the reaction is known as hydrogenation. And when we add hydrogen across the double bond, the product is an alkane. In a hydration reaction, we are adding water across a double bond, and the product will be an alcohol. So this is going to be a new functional group that we look at, a new substituent on an alkane chain. In hydrogenation, hydrogen atoms add to the carbon atoms of a double bond or triple bond. You need to use a catalyst. Remember, a catalyst will speed up the rate of reaction. It is not consumed in the reaction. Here the catalysts are metals, platinum, nickel, or palladium. You don't need all three, you simply need one of them. So we'll have our double bond, and you're going to add hydrogen to each carbon of the double bond. Let's write an equation for the hydrogenation of 1-butene using a platinum catalyst. So in hydrogenation reactions, the products are always alkanes. So here's 1-butene plus hydrogen gas. I'm going to say we have a platinum catalyst, and I'm going to add hydrogen across this double bond. Now this is a bond line structure, so we're going to take one butene and we are going to make butane. Now I just drew the hydrogens in here so you could see them, but your correct answer will just be the structure for butane without the hydrogens drawn in. Fatty acids consist of a carboxylic acid group, which we will discuss in a later chapter, on one end, and a fatty chain on the other. So the fatty chain is just a long, fat is just a long hydrocarbon chain. If we undergo a hydrogenation reaction with a double bond, we can make a saturated fat. And when we make a saturated fat, we increase the melting point. Therefore, we can have solids at room temperature, such as margarine or soft margarine and shortening, that come from unsaturated vegetable oils. Let's do a learning check. Let's write the products of each of these reactions. So here we have 2-butene. 1, 2, 3, 4. When we hydrogenate, we will make butane. Next we have cyclopentene. When we hydrogenate, we will make cyclopentane. In a hydration reaction, an alkene reacts with water, H2O, to form an alcohol. So, one hydrogen will add to one carbon of the double bond, and the OH group will add to the other carbon of the double bond. You need to have an acid catalyst, such as H2SO4, to get this reaction to take place. And so you can see here this functional group called an alcohol, which we will look at in further detail in subsequent chapters. Now I want to take note of this. It says the OH from water forms a bond with the second carbon atom in the double bond. The OH is going to add to the carbon of the double bond that has fewer hydrogen atoms attached to it, whereas the hydrogen will add to the carbon with more hydrogen atoms attached to it. Let's look at the next example to see. So here we have to predict the product of the addition of water to the following alkene. Here we have 1-butene. 1, 2, 3, 4. If we look, carbon 1 has 2 hydrogens attached to it and 1 carbon. If we now look at carbon 2, we can see carbon 2 has 1 hydrogen attached to it and 2 carbons that are directly attached to it. So the OH group is going to add here to carbon 2, and the hydrogen will add here to carbon 1, so that our final product will be the following alcohol. So an alcohol is defined by an OH group. The OH will add to the more substituted carbon or the carbon with more carbons attached to it, and the hydrogen will add to the less substituted carbon. So if I were to draw this as a bond line structure, I would have 4 carbons, and then I would have an OH group on the second carbon. Remember, we do not draw hydrogens in that are attached to carbon atoms when we use a bond line structure. We will draw the hydrogen in if it is attached to an atom other than hydrogen. So you can see the answer depicted here. So in this video, we looked at alkenes and alkynes. We learned how to characterize alkenes and alkynes. We learned how to name alkenes and alkynes. We learned about geometric isomerism in the forms of cis and trans isomers. And then we learned about addition reactions to alkenes in the form of hydrogenation and hydration.